I received an order to machine the front panel of an amplifier enclosure. It has 4 mounting holes, so I decided to go with a mounting plate approach. Since I need to make 4 of these, it makes sense to have a repeatable and secure way to hold the stock on the table. Here's the mounting plate I'll be using. I had it laser cut from 10 mm thick aluminum. To prepare it for machining, I'll face the surface and thread 4 M4 holes, which will be used to hold the stock in place. The stock was saw cut from a 200 by 10 mm aluminum bar. It's 22 mm wider and 6 mm longer than the mounting plate, so I'll cut off the extra material with a 4 mm end mill to save as much as possible. I pre-drilled all 4 pieces of stock so I can securely screw them down to the mounting plate. Since the mounting plate has M4 threads made in aluminum, I'll be using a torque wrench set to 5 Newton meters to avoid stripping the threads. This should provide more than enough clamping force for all the operations I need to perform. Here's the OP0, which will trim off the extra stock so I can save it instead of turning it into chips. For this operation, I'm using a 4mm 2-flute end mill with a DLC coating, running at 24,000 RPM. The depth of cut is set to 0.5 millimeters with a feed per tooth of 0.05 millimeters. It's not a very aggressive setup, but with such a small tool, I'd rather take my time than risk breaking it. OP0 is just about finished. It took around 15 minutes per piece. I left 4 small tabs in the middle pocket to keep the stock from falling off during machining. Now I just need to remove it gently, and for that I'll use something heavy enough to break the tabs without damaging the part. My 32mm wrench should be perfect for the job. Now I've flipped the stock around to run OP1, which will machine 2 pockets on the bottom of the part. For this operation, I'll be using a 6mm 3-flute flat end mill. I'll use an adaptive strategy to machine both pockets. The first pocket is 5 mm deep, which is relatively shallow for a 6mm end mill. It's less than 1 times the tool diameter. However, since the work holding isn't super rigid, I'm keeping it conservative with a 15% optimal load and a feed per tooth of 0.05 millimeters. This should help minimize excessive ringing during the operation. For the second pocket, I'm using the same settings as before. Since most of the stock was already removed in the previous operation, I switched to a 3D adaptive strategy. This strategy is stock aware, so by enabling the rest machining option, it starts cutting only where the previous operation left off, making the process more efficient. This design requires 90-degree corners in the pocket, so I'll be using a technique called dog bone fillets to ensure a square piece can fit properly. Dog bone fillets involve adding small rounded extensions to the corners to compensate for the radius left by the tool. Since the 6mm end mill leaves rounded corners, I'll need to make additional cuts to create these fillets. I manually drew the tool paths on a 2D sketch and used a trace operation to follow them. I'll take 4 passes, each 1 millimeter deep, to clean up the corners. This will ensure the glass insert with sharp corners fits perfectly into the pocket. Next, I'll run a 2D contour toolpath to clean up the 0.1 millimeter radial stock left after the adaptive roughing operations. For this step, I've reduced the RPM to 18,000 and set the feed per tooth to 0.025 millimeters to achieve a better surface finish. I also enabled the repeat finishing passes option to compensate for any minor tool deflection during the cut. The bottom of the part is now complete, so it's time to flip the stock and move on to OP2. This operation will machine the top of the part. There are 3 tool paths for this side: adaptive clearing, contour, and chamfer. Once these are finished, the part will be complete. The first toolpath for OP2 is a 2D adaptive clearing. Since the bottom of one of the pockets was already removed in the previous operation, it's effectively only 5 millimeters deep. I'm using the same 6 millimeter 3-flute flat end mill for this operation. This toolpath will clean up all 3 pockets. 2 of them are 10 millimeters deep, so I decided to slow down the feed per tooth to 0.025 millimeters from the previous 0.05 millimeters to avoid excessive load in the deeper pockets. The RPM remains at 24,000, and the optimal load is set to 15% of the tool diameter, which is 0.9 millimeters. Now it's time to rough out the 2 deeper pockets. At 10 millimeters, the depth is about 1.5 times the tool diameter, which is well within the capabilities of this end mill. While this isn't particularly challenging for the tool, I'd consider 2.5 times the tool diameter to be the practical limit for this setup. Now onto the third pocket. Side milling works perfectly for this round pocket. I'm using a ramping strategy with a 2-degree angle to enter the material. This is a very light load for the machine and runs smoothly, sounding just as it should. Since I'm only machining 4 of these parts, there's no point in pushing the machine to its limits. Now onto the 3D adaptive toolpath. This operation will clean up the remaining stock in the large pocket and remove the extra 1 millimeter of stock on the outside. Additionally, it will machine 1 millimeter steps into the chamfers, making it much easier for the chamfer tool by reducing the amount of material it needs to remove. The 3D adaptive toolpath is complete, and the chamfers are now roughed out, making it much easier for the chamfer tool to finish. Next, I'll run a 2D contour toolpath to remove the extra 0.1 millimeters left by the adaptive operations. I've reduced the RPM to 18,000, so the machine can move slower and leave a nice finish on the walls. Now onto the chamfer toolpath. I'm using a 12.4mm 3-flute chamfer tool to finish this part. It will remove all the stepped layers left by the 6mm flat end mill during the roughing process. The RPM is set to 12,000 with a feed per tooth of 0.025 millimeters. I'm also using the tip tool offset option, set to 1.5 millimeters to ensure the tool actually cuts the material rather than crushing it with the tip, where the surface speed is practically zero. Once this operation is complete, the part will be finished. Here is the finished part. Overall, it came out nicely. There is a bit of chatter visible in the middle where it wasn't bolted down properly. Besides that, I'm happy with the result. That is it for today. If you have any questions, please leave them in the comments. Thanks for watching and have a great day.